Hello students, welcome to Spectra Education Academy. In this video, I am continuing the explanation for short answer type questions from the chapter Potential and Capacitance. Let us continue. The first question is derive an expression for the capacitance of a parallel plate capacitor. So, capacitor is meant for storing charges. Let us say this is the first plate of the capacitor. This is the second plate of the capacitor. See, these are the two conductors. So combination is called as capacitor. Then the first one is this. First one is this. So there is small gap left between them. Then this is first plate A. First plate A is meant for storing positive charge. So continuously supplying, there are positive charges stored on this. Then this is immediately due to polarization. There will be negative charges reside close to the positive plate, close to the positive. So even in this side also, when you connect, let us say initially there will be positive charges due to polarization. When you connect this side of the plate B, right side of the plate B connected to earth, so earth continuously supply positive, negative charges because earth behaves like a zero potential body, so there will be negative charges. Negative charges will be stored. Before you connect the earth, they are all positive charges. Now, these are all negative charges. Potential between the plates of capacitor remain constant. So, this is what the principle of capacitor. Now, so coming to the explanation for the question, consider two plates. Consider two plates of a parallel plate capacitor. Parallel plate capacitor. A and B, each of area. Two plates of parallel plate capacitor, each of area A, capital A, and which are separated by distance D. Now, so this is there is application of Gauss law here. The intensity of electric field in between the two plates. Let us say you call this a region 2. We all know that this is meant for positive charges, storing positive charges. Due to positive plate, intensity of electric field is away. So this is E due to positive charge. Similarly, electric field lines move towards the negative charge. So therefore, this is intensity due to negative charges. So according to Gauss law, according to Gauss law, the intensity of electric field due to charge distribution, particularly due to positive charger plate, non-conducting charger plate. So intensity of electric field due to non-conducting plate of surface charge density is sigma is E equal to sigma by, this is E due to positive plate, E equal to sigma by 2 epsilon naught. Once you look at the midpoint between the two plates, so at the midpoint, field lines are towards the negative plate, field lines are away from the positive plate. So therefore, the directions of both field due to positive charge and field due to negative charge. So this plate is having surface charge is sigma. This plate is having surface charge density B. This plate is having surface charge density A. So intensity of electric field due to negative charge. So therefore, these two are in the same direction. According to parallelogram, once again you can say, when theta is 0, you'll get C equal to A plus B. Keeping that in mind, E net between the two plates is E due to positive plate plus E due to negative plates. But whichever may be, it may be with positive plate or negative plate, the expression remains same. Then, so sigma by 2 epsilon naught, you write sigma A by 2 epsilon naught in particular because you mentioned surface charge density of the first plate is sigma A. This is sigma B by 2 epsilon naught. In case surface charge densities are same, we can continue E net as sigma by epsilon 2 epsilon naught plus sigma by 2 epsilon naught. So taking LCM and all that, completing the calculation, you'll get sigma by epsilon naught. But you know that surface charge density is charged by area. This is divided by epsilon naught. You'll get Q by A epsilon naught. Then we know the relation between potential difference, that is delta V, electric field intensity, and the separation delta X is given by E is equal to, we call it as potential gradient in particular. Now for this particular question, for this particular case, just you write V by D. So understand that V is the potential difference between the positive plate and negative plate. D delta X is the distance between the two plates. Delta V as directly you take it as, but you treat it as potential difference only. Now, so call this is equation 1, call this is equation 2. So therefore, comparing these two, you'll get a V by D, potential difference by gap between the plates is equal to Q by A epsilon naught, V equal to QD by A epsilon naught. From the definition of capacitance, we know that when charge is given to the plate, is directly proportional to rise in potential. Keeping this in mind, Q equal to C into V. C is the proportionality constant. We call it as capacitance of the capacitor. Capacitance of the capacitor. So therefore, we can say that C is equal to Q by V. So we got V as QD by A epsilon naught. Q by QD by A epsilon naught. Q and Q get cancelled. So we'll get A epsilon naught by D. In case the gap between the plates is filled with dielectric of constant K, capacitance increases by K times. It means K into A epsilon naught by D. Now let us continue with the second question. So there is similarity. So first let us continue with the third question, because second question is the numerical which is set based on the question number 3. Even look at question number 8 also. So if you get the answer of question number 3, the same answer can be continued to get the answer for 8th question. So first let us continue with the question number 3. Afterwards, I'll continue with 8 and then I'll come back to 2. Yeah. Let us continue. Question number 3. Derive the formula for equivalent capacitance when the capacitors are connected in series. So consider 3 capacitors. Consider 3 capacitors of capacitances. Of capacitances C1, C2, C3. We can take many also. C1, C2, C3 are connected in such a manner that, let us say, this is first capacitor. It's a positive plate, it's negative plate. Negative plate of the first capacitor. Negative plate of the first capacitor is connected to positive plate of the second capacitor. Similarly, negative plate of the second capacitor is connected to positive plate of the third capacitor. Like this. In case many if you take, you can continue this. And finally, positive plate of the first capacitor and negative plate of the third capacitor are connected between the terminals of a battery, so which can produce potential difference. So this is positive terminal of the battery. This is a positive terminal. This is a negative terminal. Now this is capacitance C1, C2, C3. Yeah. So negative plate of first connected to positive plate of second capacitor. Negative plate of second connected to positive plate of third, and so on. Finally, positive plate of the first and negative plate of the last. Negative plate of the last connected across the terminals. Connected across the terminals of the battery. Now, so once battery is connected, there will be potential difference across the plates of first capacitor as V1 because potential get added. So V2 is the potential difference across the plates of second capacitor. Similarly, V3 is the potential difference across the plates of third capacitor. So charge on the plates of each capacitor remains same. So keeping that in mind, total potential of the combination, V is equal to V1 plus V2 plus V3. But remember the charge stored on each plate of the capacitor. Charge stored on the plates of each capacitor is the same, which means Q1 equal to Q equal to Q1 equal to Q2 equal to so on, Q3 equal to same, Q only. So keeping this in mind, from the definition of potential, we write C is equal to Q by V. We can say that Q is equal to CV. Now we are looking for V expression. From this, V can be written as Q by C. So therefore, V1 can be written as Q1 by C1. V2 can be written as Q2 by C2. Similarly, V3 can be written as Q3 by C3. So therefore, call this is equation 1. Call all three as equation 2, substituting all four in particular. 1, 2, 3, 4, right. So Q by C effective, because you are looking for the effective capacitance, or you can say resultant capacitance or net capacitance. So whichever the way, if you are comfort, yes, you call it as Q1 by C1, because V1 is replaced with Q1 by C1. V2 is replaced with Q2 by C2. V3 is replaced by Q3 by V3. So, but we said that Q1, all Q1, Q2, Q3 are same. So therefore, Q you can take out common. 1 by C1, 1 by C2, 1 by C3. So therefore, Q can be cancelled on both sides of the equation. So you'll retain with the 1 by C1, 1 by C2, 1 by C3. So this is the desired equation. Desired equation when capacitors are connected in series. Now let us continue with question number 8. It is mentioned that derive an expression for the effective capacitor when n capacitors are connected in series. Just everything same. Everything same. You need to continue the same answer till here. Till here. This only the thing is you need to write 1 by C1 because you have connected many. 1 by C3, so you have to connect n by C. Cn you have to call, but they mentioned that identical. They are all identical. So therefore, we write that C1 equal to C2 equal to in case if they are identical, because they did not mention directly in the question when n capacitors are connected. So therefore, in case if they are, so we'll get finally equation this only, but in case if they mention that identical, we can say that Cn equal to C. So therefore, we write that C effective as N by C. Now let us continue with the numerical bit. The numerical is given as capacitors 2 microfarad, 3 microfarad and 4 microfarad. Sorry, 3 capacitors each of this question number 2 is based on series combination. 3 capacitors, each of capacitors 9 microfarad are connected in series. What is the total capacitance? So, and second bit is what is the potential difference across each capacitor if the combination is connected with 120 volt supply. So, capacitors are connected in series means the equation for effective capacitance is, this is question number 2, 1 by C1, 1 by C2, 1 by C3. 1 by 9 micro. Micro means 10 to the power of minus 6. Okay. Plus 1 by, there is C2 also 9 microfarad because identical. 10 to the power of minus 6. Plus 1 by 9 into 10 to the power of minus 6. So LCM is anyhow 9 into 10 to the power of minus 6. 1 plus 1 plus 1. So therefore this is going to be 1 by 3 into 10 to the power of minus 6. So effective capacitance is 3 into 10 to the power of minus 6 farad. Otherwise you can say 3 microfarad. So there is another bit in the question, potential difference across each capacitor. Since this is capacitance, we need to find a total charge. Total charge is C effective into V. So what is C effective is 3 into 10 to the power of minus 6 into potential is total potential of the combination is 120. So this is going to be 360 microcoulomb because charge unit is coulomb. Now we need to find out because in series combination potential is different. But of course for this question you'll get the answer same. V1 equal to Q1 by C1 because in series combination charge stored on each on the plates of each capacitor is same. So therefore this 360 is same for all Q1, Q2, even Q3. So therefore Q1 equal to 360 into 10 to the power of minus 6 divided by capacitance. C1 is 9 into 10 to the power of minus 6. So therefore this and this get cancelled, you get 40 volts. Similarly V2, Q2 by C2 because they are identical. 360 into 10 to the power of minus 6 divided by once again 9 into 10 to the power of minus 6. So this is again 40 volts. Then V3, you don't get the answer different because all are identical. In case if they are not identical, you will get answer differently. Q3 by C3, 360 into 10 to the power of minus 6 divided by 9 into 10 to the power of minus 6. So therefore this and this get cancelled, you get 40. Yeah, so there is another question also connected in series, but it is mentioned that 100 volts. The same procedure you have to follow. Thank you very much, students, for watching my video. In the next video, I'll continue with explanation for parallel combination of capacitors, effective capacitance first. Then thereafter, I'll continue with the numerical based on parallel combination of capacitors. Thank you, students, once again. But don't forget to share and subscribe with your friends and relatives.